be talking about composite timber structures. So I put out a little phrase there about timber concrete composites, but it's going to be a much larger discussion than just that. So today what I want to talk to you about is composite structures kind of in generalities, then talk to you about composite timber structures, and then lastly talk to you about our research and how we've been trying to use composite timber structures to get buildings built that are outside of current code limits. So let's start by talking about an easy composite element. So this is composite metal deck flooring. So here you've got a corrugated metal deck with some perforations and a concrete topping slab on it. Well, the two are bonded together and act together. Why is that? Well, because it makes it stronger, it gives it an acoustic rating, and it gives it a fire rating. So those two materials combined give you a very strong floor structure. But then the floor structure itself is supported by beams. Well, now you've already got the concrete topping slab on the floor to solve strength, acoustics, and fire. So you might as well go ahead and attach that steel beam to the concrete deck with shear studs, making it a composite steel beam. The same thing can be done with studs on a steel truss to make a composite steel truss. And what are they supported by? Well, columns. Let's say you've got a steel column and you need a higher load-bearing capacity. Maybe you wrap it in concrete. Maybe you need a higher fire rating resistance, so you wrap it in concrete. Or maybe you've got a tube and you need more capacity, so you fill it with concrete and go the opposite direction. But the idea is you're using one material to strengthen the weaknesses of another material. And by doing that, you can get more efficient structures. Now, this doesn't apply just on an elemental scale. It can also happen on a building scale. So this is what I would call a composite building structure. So this is structural steel framing and a reinforced concrete core. They don't act together, so it's not composite per se, but using two dissimilar materials in a building, two different trades, is considered a composite structure. It's kind of interesting where we draw these lines on when something is composite versus not. So this is an image of the Willis Tower, Sears Tower, that was designed by our firm SOM. It is still the tallest structural steel building in the world. But what's something that's kind of funny about that is it consists of 75,000 tons of structural steel and 100,000 tons of concrete. And the only concrete in there is a thin composite metal deck slab. So when you look at it on paper, the tallest steel building in the world is less than half steel. So those lines are kind of arbitrary to some degree. So why do people choose composite structures and composite elements? Well, strength and stiffness are a key. Concrete is really strong in compression. Steel is good in flexure. So based on your requirements, you might pick one or the other or combine them. But mass is also an issue. Maybe you've got an uplift problem, so you want something heavier, so you choose concrete. But then lastly, what about acoustics and fire? Like we talked about the metal deck slab, without the concrete topping slab, you'd have to fireproof the bottom, put cement board over the top, and then an acoustic treatment on that, and make the gauge much thicker to make your span. You'd never do that. So you pour the concrete on it to solve the structure, the acoustics, and the fire. Well, these are all really symptoms. They're not the real problem. The problem is cost. We're trying to drive down the cost of our structures and make them more economical for our clients. And these are just the line items on how we get to cost. So composites, much like anything else in engineering, it's really about economics. So how can we learn from what other people are doing? Now, this building I'm showing you is an example that I'm currently working on. It's in the planning phase in Boston. And if you know anything about Boston, it's been known for a very long time as a steel town. So if anything can be built in that building out of structural steel, it will be. Very strong unions, very strong trades, a very competitive market for concrete to get into. But because of the strength and the stiffness of reinforced concrete cores, they're actually coming to the forefront so that even in a town like Boston, a reinforced concrete core and a composite solution is becoming more economical. What can we learn from that? So let's talk about timber and how timber can benefit from a composite approach. The first and easiest thing is talking about topping slabs. So just like the metal deck, you need to have something that gives you your acoustics, fire rating. So if you make a composite with these little screws that are shown here, you can get a floor structure that spans longer, has a higher acoustic rating, and a higher fire rating by making a composite. So why wouldn't we do that? You've already got to put the material in the building. Why don't you use it? Now there's other things as well. You can talk about using it in a beam configuration. Again, once you've already got it in the floor structure for acoustics and fire, why don't you connect it to the glue lam beam, and just like you've got a composite steel beam, you got a composite glue lam beam. Now, it's not just about concretes, and that's why I try to walk back the title of my presentation, and I just pulled this paper from the World Conference on Timber Engineering in 2010, because it's a good example of showing how structural steel can be used in conjunction with timber. Now, in this application, it's kind of backwards, because you want to protect the steel from fire and to use the insulating quality of timber. So by having a steel core wrapped in timber, you actually enhance the fire rating of the steel and give a high strain capacity in sections that are needed. Again, this can happen on a building scale. So this is the Bullitt Center, very well known as a successful timber building. But if you think about this building, it's got the NLT decks and the glulam beams, but on the lower left-hand corner you see there, it's got a structural steel braced frame because it's a high seismic area and you want a high degree of seismic resistance. So you're mixing it in. In addition, it has a 3-inch thick acoustic concrete topping slab. So when you look at this building, it's actually got quite a bit of all these materials. The same thing can be said about LCT1, concrete core, glulam, concrete decks. Very much a composite building. So now that you know what we're talking about when we talk about composites and what that means, let's try and frame out what some of these different things are. For the purists, an all-timber building would be an all-CLT building with a dry acoustical treatment like mineral wool and sleepers. For the purists, an all-steel building would be like a Costco. So that'd be a structural steel frame with a tin roof on it, no concrete. And concrete is pretty simple, it's just concrete. But most buildings don't operate in these corners. They operate in this field here. So filling it out, you can see where the Bullitt Center lands. You can see where LCT1 lands. You can see where typical structural steel lands, and structural steel with composite cores. Now in the upper right-hand corner, there's another dot there for SOM's concrete jointed timber frame system. And that's what I'll talk to you about next. How do we leverage composite ideas to get a higher level of performance and push the bounds of timber construction? So for those of you who are not aware, we did this research project 3 years ago. It's available on SOM.com, so you can download it free of charge and take a look through it. It was a study of high-rise buildings and how we could develop structural systems to support buildings up to 42 stories. Now, 42 stories is very specific, and there's no magic associated with it. What we wanted to do is pair it against a very competitive building that we had done in the past, so we could do a one-to-one comparison on how much concrete this building took and how much would it take in timber. That's the real system. Now, to paraphrase and go to the executive statement on the project, you've got this amount of sentences kind of trying to tell you what we're up to. And I want to just highlight a few words for you. The goal of the research project was not to support a 42-story timber building. It was to develop a structural system for tall buildings, all kinds of tall buildings, that uses mass timber as the main structural material, not necessarily the only material. But most importantly, it needs to be able to compete with concrete and steel. If it cannot compete with concrete and steel, it won't matter how much you reduce your carbon footprint because nobody's going to be building them on a large scale to matter. We came up with 2 different solutions. On the right-hand side is a solution for a 42-story all-timber building. On the left-hand side is a solution for a 42-story composite timber building. And when you compare the two, there's some real things that jump out at you. How many columns? How many walls? How flexible is that space long-term? And it's pretty clear looking at the two that the composite solution is more flexible and more friendly for clients. So this building ourselves, we looked at it and said, okay, how are we going to join these things together? And this is the main thing that we documented. And effectively what it is it's cross-laminated timber floor planks, cross-laminated timber shear walls, glue-laminated columns, but they never touch each other. The thing that's connecting them all is a little bit of reinforced concrete that runs around and joins them all together. That's a little bit weird. People don't see that coming. This is what it would look like in sections. So on the left-hand side, you've got a timber shear wall and a timber floor connected by reinforced concrete. On the right-hand side, you've got a glulam column and a timber floor connected by reinforced concrete. Why are you doing that? Well, when you think about mass timber, it's very much like precast concrete. And if you've ever designed a precast concrete building, there's 2 ways to connect precast elements. There's the dry connection, where you have exposed structural steel connectors and you bolt them together, or you weld them together and fireproof or grout them. Or you do a wet connection, where you have a piece of precast with dowels hanging out, and you put them next to each other and cast the overlapping dowels to make it good in the field. It's called a wet connection. So effectively what we were proposing on our 42-story timber building was a precast building with wet connections, but by the way, there's no precast, it's all timber. That's the way to think about it. And what we found is by using this approach, we really could compete in terms of materials consumed, but also carbon footprint. we showed that this building would reduce the carbon footprint by 65 to 75% by using this composite timber system. So very competitive. So what did we do with that after we finished off? Well, we said, let's try and get this into real buildings now. And what could that mean? So this is a proposal that we gave to a client who was interested in doing a 12-story residential building. On the left-hand side is a conventional all CLT solution for the main residential levels and a concrete transfer slab and a concrete structure at ground level. It's pretty cumbersome. It's not very flexible. It's not very friendly long-term. So if your units change during the construction process or design process, or if it starts out as apartments and goes condos and you want to buy out your neighboring unit, it's really hard to change that long-term. On the right-hand side is utilizing our composite approach for that same problem. And by doing this, we can actually get a column grid, which is equivalent to a concrete building. And by the way, it's actually using fewer overall materials. We think that can be competitive. In addition, we talked to contractors and we said, what do you like about this? What do you don't like about this? Don't read this slide. It's meant to show you there's a laundry list of things that contractors didn't like. So we took that to heart and we said, okay, let's try and solve some of these issues as we go forward. We also wanted to take a look at what really matters in terms of reducing carbon footprints. So if you think about a building, almost all of the material, about 2/3 to 3/4, comes from the floor structure. Actually, a very small percentage, like 15 to 25%, comes from the timber shear walls. But there's a difference when you kind of consider these things. A timber shear wall is only going to be used in a timber building. I don't ever see you doing a concrete flat plate supported with CLT shear walls. Why would you do that? But a timber floor is different, because you can use a timber floor in a timber building. You can use a timber floor in a precast concrete building. You can use a timber floor in a cast-in-place concrete building. You can use a timber floor in a structural steel framed building. So not only does it take up the most materials in a project, coming back and thinking about Sears Tower, but you can also use it with a whole host of different framing systems. And that's how you really push the needle in terms of sustainability on a societal scale. So that's what we did. So this was the second research project that we put out, again, available at som.com, and we really honed in on the floor structure, saying that's the biggest get in all of this. So the first thing we did on the upper right-hand corner is we took this non-structural acoustic concrete topping slab, and we made it structural and composite. Again, it comes down to one very simple thing, okay? Don't waste material. If you are going to pour concrete in your building, make it structural and composite and get some savings elsewhere. But we did it for another reason as well. And that's because of the fire rating. So these are the test results from the CLT handbook. It's 5 floor tests. One didn't go all the way through to completion because the test frame failed. But of the remaining 4 floor tests, 3 out of the 4 failures were integrity, which means the structure was strong enough to span it after losing cross-section and charring. The timber was good enough to insulate it so you didn't get heat gain on the other side. But because of the joints in between the panels, it allowed fire to pass through and ignite on the other side. So by doing a composite structural concrete topping slab, you basically create a line of defense that says you can't go past here. And recently in the upper right-hand side, you see some fire tests using nail laminated timber and cross-laminated timber with composite concrete topping slabs. Fire ratings of 3.5 hours on a floor. If you're doing a type 1A construction building, generally speaking, you need a 2-hour fire rating on your floor. This can give you 3.5. So if you're talking about taking something outside the scope of the code, it's wise to start there from a position of strength. It also allows us to do something else. So this is a rendering of our initial system. And it shows you kind of what we're doing. It's got the concrete connections in there that are exposed. And as an engineer, that's okay. As an architect, it's not okay. It was one of the largest complaints we had, which is we don't mind the composite system. I just don't want to see it. I want the total timber, aesthetic. So by making that topping slab composite, what we were actually able to do is take the portions that were precast and make them timber. So what that allows you to do is basically have a continuous timber soffit with all the concrete on top. Now it would look like that. So this is our latest system that we're working towards, where the only materials are mass timber and cast-in-place concrete. All the timber's on the bottom, all the concrete's on the top. So it's kind of like this Schrodinger's cat situation, whereas if you can't see the concrete, is it really there? From an aesthetic perspective, no, it's not. So it solves a lot of problems from the architectural side. But what else? Okay, we can't ignore all the other issues. What are the other risks associated with doing a high-rise timber building? Well, we developed this little chart for a client of ours who was looking at doing a high-rise timber building in a seismically active area. And what we tried to identify for them, where the real risks were. And if you think about the risks, there's 2 things. There's the consequence and the likelihood. or the severity and the probability. So a fire is a very severe thing, but it's kind of rare. They don't happen all the time. But for this particular building, located in the Cascadia subduction zone, earthquakes were at the top. Because guess what? An earthquake will test that building if it survives its design life. So how can we reduce the issues of earthquakes? Well, you can do some project-specific testing, but that can impact the schedule. Or you can give it a concrete core. It's kind of like the dumb guy solution. It says, okay, well, if earthquakes are the problem, let's give it an approved seismic resisting system. Now, the other benefit of that is it's coming back to fire resistance. So now that you've got this composite timber floor that can give you a 3.5-hour fire rating, combined with a reinforced concrete core, it gives you a complete non-combustible egress path, reducing any life safety challenges associated with the building, because all you got to do is get to the core. Then you've satisfied egress, you've got an area of refuge, and it's only a property damage issue from there on out. Now in the upper right corner, we're showing another little trick where what we've done is we've taken that concrete topping slab and we've detailed it in such a way that reinforced concrete is what supports the facade. And in doing that, we can actually use all approved fire-stopping materials at the facade. That's the next weak link in letting fire pass to the next level, is the facade. So using this composite approach, it lets us kind of sidestep and move around some of the challenges that are definitely solvable in all timber building. But the question is, when you solve it, can you be competitive with concrete and steel long term? That's the question. So what do we call this thing? Well, I've suggested it to a number of clients now, and we're working forward with some of them. And we call it our model composite timber building, because someone comes up and they say, we want to do a high-rise timber building. Hey, let's do this thing. We want to do a high-rise apartment building. Hey, let's do this thing. We suggested it a number of times. We keep coming back to it. It is 2/3 timber and 1/3 concrete. So 2 parts timber, 1 part concrete. It's kind of okay. It's still mostly timber. It has reinforced concrete shear walls and a floor that's got a reinforced concrete topping slab for fire resistance. So what are the benefits of using this approach? Well, first and foremost, it's structural. By getting that composite topping slab, we can get the long spans on the columns. By having a concrete diaphragm, we've got a non-combustible way to get seismic loads into the core. So it's a load path of concrete slab to concrete core to concrete foundations to ground. And that gives people a certain amount of reassurance if they're not ready to take on the risk. We've also got the topping slabs on there for acoustics and durability long term. And we also do it to enhance the impacts on other trades. So by using a reinforced concrete core, now you haven't changed anything about the elevator manufacturer or supplier. You haven't changed anything about the stair manufacturer. And if you get smart about how you detail the perimeter of your building, you haven't changed anything about how you detail and attach the facade. And in fact, the only thing that you've changed is you've made the MEP guy's life easier because he's just attaching into wood, and you made the partition guy's life easier because he's attaching into wood. But lastly, it's about fire. We talked about the risk and how for some buildings, fire is not the real risk. But the conversation is always going to start and stop there. And that's what this is really all about. By giving the concrete cores, you've got non-combustible egress path and areas of refuge. You've got non-combustible facades, non-combustible partitions. You've got encapsulation only where necessary, and fire ratings that can rival Type 1A construction. That's a pretty solid position to be in if you're going to try and go outside the bounds of the code. So how can we classify this thing? What are we going to call this thing? So it will never be Type 1 construction because it will always have combustible pieces in it. So we don't think that's a winning battle to say that it is Type 1 construction. The easiest thing is to call it Type 4 heavy timber construction and saying it's a subset of that. But when you really think about it, it's not heavy timber. We've done all of these different things to it, the concrete cores, the topping slabs, the detailing, the care with all of these different things. And that's what the code is set up about. When your type of construction is more fire resistant, you're awarded with some additional height and area. And it's kind of funny because it's at this time when people that like the all timber building, kind of get pumped up a little bit and say, well, this is not a timber building anymore. We're talking about timber buildings. And we're kind of like, yeah, that's the point. This is something different. And in fact, what we would suggest is something like the following. So we haven't had a new type of construction in the building codes for about 80 years. It's always been Type 1, Type 2, Type 3. But now that we're talking about this mixture of combustible and non-combustible, we actually think it's time to define a new type of construction. So instead of Type 4 heavy timber construction, why don't we push for a Type 4 composite timber construction? And because it's got enhancements about its fire resistance, why don't we reward it as the code does with other types of construction? Additional height and area. So I've just done a copy and paste over from the type 1B over and photoshopped it in. There's nothing fancy about the slide. Okay? So moving forward, how do we advance this? From our perspective, we think it's a really good thing to do, so we want to test it. Yes, we want to build it, and we think we know enough that we can build it now, but by testing it, we can make it more economical with that goal of making it competitive. So right now what we're doing is we're engaged with Oregon State University in doing a full-scale destructive structural testing on our proposed components of our next generation scheme. That's what's shown up here. And it's by no surprise that the model building we're using to model it is an 11-story building with areas way outside what you could do with heavy timber building. It's exactly what we're trying to do. And we just take a slice out of that floor section, and we're going to break it full scale to confirm that it works. So I wasn't here yesterday, because as soon as I landed, I got in a car and cruised down to OSU to check it out. So the pano shot on the top is their main section of the lab. It is a long tsunami tank is what's in the middle there. They got a whole lot of different things going on, reinforced concrete columns being reinforced with titanium. They're looking at durability of precast, pre-stressed utility poles. They've got atmospheric testing and all these things. And all the way down on the very right, you've got our lowly timber planks ready to go. So all the material's there. The contractor is on board to start the construction on the specimens Monday. Now, when we started working with OSU, we said we needed to get it going as quickly as possible. The testing should be done sometime in the summer to late summer. The results should be post-processed no later than fall. Now, to bring it back, we think that we can build these things now, but by doing the testing, it's going to allow us to make our timber panels a little bit thinner, reduce the number of screws, because again, at the end of the day, it's all about being competitive. So conclusions. Let's bring it back to the 42-story study and why we did it. Because I think it kind of makes a little bit more sense once you see what we're trying to do with that work. The goal is to develop a structural system for tall buildings, all buildings. And that's what we're pushing forward now with OSU. But at the end of the day, it's got to be competitive, it's got to be competitive, it's got to be competitive. And that's why we've gone to this, this composite approach. We think it's the right way to go when you're trying to push the limits of the code. Got it, right at the same time. So thank you.